just wanted to go through what we have covered so far very quickly here. So, we would continue from where we stopped, and that thing is not helping at all. Okay, finally it's responded. It was doing something else in the background. All right, well, good morning. You have any questions before we get started? Okay. Well, so far we talked about the solution of the transmission line problem. I don't know if this thing is going to cooperate or not. Let me see if I can open the PDF version. Maybe that will go faster. Okay. I want to get a couple of graphs here. I give up. I'm not going to do that. Let's just close this and open the PDF version. Yeah, we got that. So we talked about standing waves, and we talked about the issues that standing waves will cause. Basically, they take place or they occur as a result of mismatches on the line. So it's important to get rid of reflections and achieve matching. And we said matching actually has two versions of it. A version for maximum power delivery, which requires that the load be the conjugate of the source, while the matching in terms of no reflections implies that the source and the load must equal in impedances. So obviously to be able to meet the two constraints simultaneously, you would like to work with pure resistive circuits. If you have pure resistive impedances, like the characteristic impedance is pure resistive, the source impedance is pure resistive, the load impedance is pure resistive, then you can achieve both conditions at the same time. And that obviously works out very well because transmission lines that have pure resistive characteristic impedance mean they are lossless, right? We mentioned that. So lossless lines will have a pure resistive Z0, and you can make both the load and the source equal to that. We haven't talked about how to do matching yet. We'll talk about that hopefully today. We'll get started with that. When we have standing waves, as a result of the mismatches, the signal amplitude, is that before or after the figure that I'm looking for? Looks like it's after. Yeah, it's later in the chapter. There we go, right? That's a typical standing wave behavior in a low loss line, all right? As you can see, if it was lossless line, then you have no changes in amplitude, and if it's a traveling wave, you get that. If it's a pure standing wave, you get that. If it is a mixed wave, in other words, you got some part traveling and part standing, you get this, right? Now, if you have a lossy or a partial loss, you get things to decay this way. This one here, obviously, it will never be pure standing wave in this case. In a lossy line, you'll never get a pure standing wave. You always get some mixed wave. So you get this kind of situation where the asymptotes here are like this. This is like your traveling wave part. That's your like standing wave part. And the combination will be like your mixed wave. There will be maximums and minimums. Here, the maximum and minimum are the same amplitude. So Vmax and Vmin are the same everywhere along the Z line, like the Vmax here, and Vmin is 0. Here, there's Vmax is equal to Vmin. It's the same thing, it doesn't change at all. Here, the amplitude is always changing down the distance of the line, that's your Z coordinate. And Vmax and Vmin are both changing here. Now, in the commercial world, we like to give a feel for how much standing wave do we have on the line by defining what we call the standing wave ratio, SWR. That's SWR number is typically one of the specs in transmission line components or impedances in general. So they give you a device and they tell you the standing wave ratio is that much. So that's a number that is typically given, and it's defined simply by the ratio of Vmax over Vmin. In this case here, it's easy to define. In this case here, SWR is infinity. SWR here is 1. SWR here is equal some number between 1 and infinity. Alright? So your SWR is 1.1. Oh, that's very good. We are very close to that. SWR is 20. Oh, we are too far away from matching condition. So when the number is closer to 1, that means your device is close to matching and your traveling wave is the dominant component there. That's a typical definition here. Obviously, the real world is like this. Okay? And the definition of SWR is typically given close to the load, right there. Right? With the loss, the way you see things here, the SWR is a much better number. Right? The curves shrink, and the ratio here is at maximum close to the load, and that's where we define the SWR typically. You take the first max and the first min, and people would realize that this is really the worst case that you can have, the standing wave ratio. Now, if you look at Vmax and Vmin, going back to the lossless case, I believe that will be the page before that. We have a figure here that's not coming through. There it is. Okay? See this figure right here? Okay? That's your Vmax and that's your Vmin. If I go back to the phasors, there is some of that. You remember the phasors diagram that we mapped at one time? That was your V plus and that was your V minus. And Vmax took place when V plus was equal to, and V minus were along the same phase. So that's your V max. And V min happened in this location here when V max and V min subtracted from each other. So V min is actually V plus minus V minus. Okay? That's in the lossless case. I'm not adding the attenuation factor here. We said it would be a secondary effect anyway. So in this case here, I can rewrite this one here as V plus V minus divided by V plus minus V minus. And with the definition of gamma 0, that would be equal to 1 plus gamma 1 minus gamma. It doesn't matter whether we are talking about gamma at 0 or gamma at L, because in a lossless situation, if you remember, let's write gamma. Gamma of Z was equal to what? V minus e to the plus gamma Z divided by V plus e to the minus gamma Z. And if you say lossless, that would be V minus e to the plus j beta z divided by V plus e to the minus j beta z. And if I take the magnitude here, the magnitude there is equal to V minus over V plus magnitude everywhere. In other words, your gamma would be the same magnitude anywhere on the line. Alright? So this gamma here would be either any gamma on the line, because they are all the same magnitude. Okay? Should be gamma magnitude is gamma of 0 is gamma of z magnitude is the same as gamma sub L magnitude. It's the same way everywhere. Okay? And sure enough, you know, if gamma is the same, your SWR is the same everywhere, and that's the lossless case. You know, the V plus and V minus have the same magnitudes everywhere, and therefore the gamma have the same magnitude, and the standing wave ratio is the same magnitude everywhere. So 1 plus gamma over 1 minus gamma. Okay? Now, you can write gamma magnitude as a result as SWR minus 1 divided by SWR plus 1. Right? This relationship, that pair of relationships are always alternate way of presenting the same thing. This is equal to that, then this is equal to that. If you work out the equations, you can derive this one here. Remember what gamma was? Was Z of Z, if you write gamma of Z, for example. Z of Z minus Z naught divided by Z of Z plus Z naught, which can be written as Z of Z over Z naught minus 1 divided by Z of Z over Z naught plus 1. See the similarity between equations here. Alright? Gamma of Z magnitude is equal to SWR minus 1 divided by that. Gamma of Z is equal to the normalized impedance minus 1 divided by that. The similarity implies that if Z of Z is real, alright, if this is real, obviously that would be the same as that. So whenever Z of Z is real, the normalized impedance is the same as the standing wave ratio. Right? The locations where Z of Z is real, the normalized impedance is real, then the equations are identical. And actually, that's the explanation that we'll see later in the Smith chart. And if you see the scale down here, let me expand this. We'll get to that at some point, and you'll see that scale on the Smith chart, which gives you the reflection coefficient magnitude versus standing wave ratio, and you will see a third line on that, which is related to the impedance. There is that similarity in equations, and it is a useful relationship to observe. All right, so with that done, we move now on to two things that we need to do. One of them is how to match, and next is then with the bounce diagram. Actually, three things, and the third would be the Smith chart. So these are the upcoming things. How to match, that's number one. Number two, bounce diagrams. Number three, the Smith chart. Okay? With that, we would conclude our discussion of transmission lines. We discussed signal delivery and power delivery, and we talked about the combined power and signal delivery constraints. And then we talked about impedance, the driving point impedance, and we showed some of the special cases: open circuit, short circuit, lambda by 4 line, lambda by 2 line. Impedance matching is our next topic. Okay? Why do we need matching? We discussed that already. Okay? We need good quality signal delivered, especially in communication systems, and obviously also it's affiliated with the best power delivery to the load. So I'm going to turn the projector off, but before I do that, basically to do matching, if you have a source and a load, we need a matching network in between, right? That's typically the situation. And that matching network would be simply thought of as an impedance transformer that transfers the ratio of the impedance from one value to another. Anything that transfers the impedance level is a matching network. And in low frequency circuits, we simply wind a transformer. We have a primary and a secondary, and we know that the turns ratio would get you the impedance levels, right? If the voltage ratio or the turns ratio is n, the impedance ratio becomes n squared. Now these are typical simple circuits that you can do impedance matching with. You can see right away, if I add a series impedance or a shunt impedance, that will change the impedance level, right? Right away, you know. But can we do good quality matching with a single impedance like that? As it turns out that this is so limiting, because typically if you have a change in the reactance level, you can add a reactance to achieve that. But if you have a change in resistance level, that means these components have to contain resistances. Like if this is a 50 ohm line and you want to see a 75, that means you have to add a 25 ohm resistance there. That means you are dissipating power here. You have a voltage divider and also a power divider, because your power here is going to be divided between the resistive here and resistance there. If it's a reactance, it's okay. Add a reactance, no problem. Reactances don't dissipate power. But if it's a resistance level, then this is a disaster here. You can change your impedance levels, but you are wasting power. So we don't do that. So we go to the next step of fanciness, all right? And what we call the left side here is typically called the L section, and the middle one is called the pi section, and the right one is called the T section. And these are typically used in radio frequencies, right? Very commonly used in radio frequencies. You use L and C, all right? These are typically O reactances. And the surprising thing, although that they are O reactances, they can change the resistive level as well, okay? And you can prove that. You can see lots of paper written on this, and references, and those of you who study radio engineering have seen that an L and C here, or C and L, depend what you want to do, you can change your impedance level very nicely. But in transmission lines, we can't use discrete components, right? We can't build a discrete, we cannot wind a coil, all right? at these high frequencies, these ideas are not good enough. So what we do is we use transmission lines to play the trick. If transmission lines have a varying impedance as you go from one place to another, Z of Z is equal to, and you recall it's a function of Z, that means if I go from one place to another, the impedance Z of Z1, Z of Z2 are different. So I can change the impedance as I move down the line. So if I can change the impedance as I move down the line, so why not use transmission lines to provide the impedance level matching that we require? So what we do is typically, that's a mismatched line, mismatched termination. I move down the line until I get close enough to the matching such that I add a reactance, and now I have matching. Can do the same thing by a shunt or a series. So I'm back to adding a series or a shunt elements, but not as the only element in the circuit. I'm combining that series or shunt element of reactance along with a piece of transmission line. So the transmission line will do part of the game, and the reactance will do the second part, and the combination will achieve the matching. All right? So that is what we do in transmission lines. We call this the series stub or the shunt stub approach, because that reactance typically comes from another transmission line, and that reactance here is also another transmission line, and you'll see the picture coming next. Here we go. So that's how we do it. That piece of reactance came from another transmission line here, and that reactance also came from a transmission line. And you notice I'm using a short circuit line, all right? I'm not using an open circuit. Although you can use an open in principle, mathematically, but in the physical world, we indicated that a shorted line is more practical in realization than the open circuit line. So you add another transmission line like that, and the combination of the location of this that I chose on my line and the length of this, the combination of these two can get me a good matching right here. So if you have a ZL here, you reach a level here where you have a certain characteristic of that impedance, you add that reactance, the combination here becomes your Z input is equal to RS, so it's matched to your source impedance. Same thing here. You move down the line, your ZL and Z of Z changes until it comes to a certain characteristic here, and when add that reactance, you end up with, again, Z input is equal to R sub S. These are two options. Which one we like more? Obviously, the shunt one is better than the series one. We discussed that at high frequencies, you always would like to have a ground in your circuit. We don't like floating components. This one here is a floating component, it doesn't have a ground. This one here has a ground, right? Especially if you're building that in a certain planar geometry, for example, all right? And you have the ground plane is your substrate, right? So obviously, to build that, is going to be a different layer of construction. Well, this one here is easy because it contains the same ground plane as your substrate. But anyway, we can say that we have 4 options here. When you think about it, 4 configurations. Mathematically, you start with your impedance of the load, you move down the load until a certain location here, we call it Z sub D, and then I can add either a series stop or a shunt stop. And in this case here, the stub is open circuit. I can do the same thing with a series stub that is shorted. Or a shunt stub that is shorted. You have 4 mathematical solutions. And you can design for any one of these 4. Now this one here is the one that we prefer practically, but nevertheless, that you should be able to compute all these. Yes, sir.
Oh, sorry, I was just gonna ask, does that also achieve matching at the load? But I mean, it matches at the source, because Cn is equal to Rs, but how is it matched at the load?
Basically, all right, if you match the source, that means there are more reflections here, and that your signal that you derive from the source is the maximum, all right? And that's really the whole object. Now, this distance here is typically very short, right? Although I'm showing it kind of, this stub here is so close to the load as possible. You don't, as you know, that the impedance here repeats every lambda over 2, all right? So a better picture of this is obviously to put this somewhere in here and show this one here, the maximum. So your source will be sitting somewhere, all right? And your load is over there, and we come as close as we can to the load and put that stub. So the majority of your line is matched, all right? And you are drawing the most signal out of your source accordingly. Now, if there is a particular application that you'd like to do the opposite, then you do your calculation from the other side, all right? Then you start here and you try to make the impedance match to the load in the opposite way and minimize the distance where it's mismatched. Okay, so where is that location? Mathematically, I'm going to do one of those. And the others are done in a similar fashion. Let's do this one here. So this is location D, that's distance D, and that's Z of D, that's Z sub L, and I can write Z of D is equal to Z naught times Z sub L plus Z naught hyperbolic cotangent of gamma D. Down here is Z naught plus Z sub L hyperbolic cotangent of gamma D. Okay? That's the impedance right here. And then the impedance of the stub, Z of the stub, is equal to, it's a similar equation, Z naught of the stub. Now this is Z naught of the line, okay? Z naught of the line, Z naught of the line. This is Z naught of the line. Because the stub could be a different characteristic impedance, different dimensions for any reason. So we'll just make it general. Your ZL in this case is a 0. You have a short circuit plus Z naught of the stub. Upward tangent of gamma of the stub times L of the stub. The stub here will be LS, and we'll have a gamma stub. This was gamma of the line as well, if you would like to be specific. Divided by Z naught of the stub plus 0, because ZL of the stub is 0. Obviously, this cancels that, and that's the expression that we have. As you can see, is the tangent function that give you a reactance only, right? If this is going to be so small, low loss, so that's equal to Z naught stub with a J, tangent of beta of the stub times L of the stub. As you can see, it's a pure reactance. You want to call it JX stub, that's fine. Because that's actually a resistive value. Z naught of the stub is R naught of the stub because it's a lossless or low loss anyway. The sum of these two, the impedance here, Z input is the sum of these two. So Z input, which would like to be R of the source, is equal to the sum Zs plus Zd. Zs is right there, Jxs plus Zd. What do we conclude? We conclude that a resistive is equal to that. That means if I break this into R sub d plus Jx sub d, the R sub d must equal to R sub s. And the Jxs plus Jxd must equal to 0. What does that mean? That means I move down the line and I monitor the real part of the impedance. I move down the line until I see the resistive part of Z sub d is equal to R sub s. Because I have to meet that. We said the impedance changes, right? So I keep moving and I monitor the real part. When the real part is equal to R sub s, I stop. I say that's my location. I got the resistive part met. And I look at the reactance part here and I say that's how much I need to tune out. That's how much stub I need. So at that location, I look at XD and I negate that and I say that's my X stub. That's my second step. Calculate how much stub I need. I need that much stub to tune out this. And based on the X stub, I go back to this expression and find my L stub. Chuck is whistling too much today. So these are the steps that we do. Obviously, you can write a simple code to do that computation. All right. Go back to this expression here and equate that to R sub s, the real part of this. And from there, find D. Find that this is D and X sub D and the corresponding X sub D. So that's step number 1, which is right there. Step number 2 is get X sub S. Step number 3, find L sub S from there. That's your 3-step matching mathematically. We'll do that on the Smith chart and you will see it makes sense. And it's a simple thing that we do over there. We've done that, and we have a matching network now that is control geometry, all transmission line. Question?
So the RS is the source resistance?
Yes, the source resistance. Yeah, we said we are working with all pure resistive source. The load may not be resistive, but we can control the source resistance. We build that source, so we can control that part. The load could be anything, but we can work things out that way. Okay? So that's the solution for this case. This is no different all what you need to do is just work that with an infinite impedance here. You work this one here as infinity, which requires that your expression here will be cotangent instead of tangent, all right? That's all what's going to be different here is you work with cotangent instead of tangent. You must be reading this chapter here because it has all these things in adequate detail. Another option is obviously using the half wave and the quarter wave transmission lines. We talked about that last lecture. And the quarter wave transmission line have this, where is it? Yeah, that's the lambda by 4 line. This thing here jumps instead of moves smoothly. That's a half wave. Where's the quarter wave equation? It's going to be up. Better find me a better machine here. See, that's the quarter wave transmission line. Rs is equal to R naught squared over ZL. Obviously, that's not going to happen unless your ZL is pure resistive, right? So you can't use that unless both of them are resistive. So in this case here, your R naught will be simply of the quarter wave line will be simply the square root of Rs and RL. The half wave transmission line will used to be matched when the two impedances are the same, but the matching section between is different, like we said before. Okay, so that's matching. Bounce diagram. We leave that here, and let's talk about the bounce diagram. Any questions about matching? Okay. That will be an experiment in the lab that you will work out, and you will design a matching section, and you will put it to test, and you will see how difficult it is sometimes to get that perfect matching.